This is the first part of a three-part video on the Shapley value. The Shapley value was named in honor of Lloyd Shapley, who was an American mathematician / economist who won the Nobel Prize for Economics in 2012. He introduced the concept in his 1952 article, which was called A Value for In-Person Games, of which you can see a copy here. You can easily find it on the internet, and it's also quite readable, so I highly recommend you to do so if you're interested in the topic. The Shapley value determines for each coalitional game a division of the value of the grand coalition among its various members. Shapley does this by introducing some desirable properties, which we will call axioms. And he then shows in his paper that for each coalitional game, there's a unique division rule that satisfies these axioms. And this division rule is now called the Shapley value. The Shapley value is not only used a lot in economics, but also in other fields. For example, it is frequently used in machine learning models in order to explain the contribution of various features in the prediction of highly nonlinear models. So in the first video, I'm going to explain to you the concept of a coalitional game, and I'm going to introduce you to the Shapley value and tell you how we can compute it. In the second video, I'm going to present the 4 axioms, which are slight variations on the one that Shapley presented in his own paper, and I will show that the Shapley value indeed satisfies these axioms. And then finally, in the third video, I will probably be a bit more technical, and I'm going to demonstrate to you that the Shapley value is in fact the only division rule that satisfies these axioms. I'm going to start by defining a coalitional game. So for a coalitional game, we need 2 ingredients. The first one is a set of players, which we will denote here by n, capital N. So here we will have small n number of players, 1, 2, up to n. And a subset of n we'll call a coalition. Okay. And then the second ingredient of a coalitional game is a value function v. And v determines a value for every possible coalition S. Okay, so S is a subset of n as a coalition, and v of S gives you a number, it's a real value number, gives a number for every possible coalition of S. And we take as a given that the value of the empty coalition, is equal to 0. So here I have an example. We have 3 players, 1, 2, and 3. The value of the empty coalition is 0 by definition. And then here the value of the singleton player 1 is equal to 2. The value of the singleton 2 is equal to 3. The value of the singleton 3 is equal to 1. Coalition 1 and 2 together can obtain a value of 7. 1 and 3 together can obtain a value of 4. 2 and 3 together can obtain a value of 5. And finally, the grand coalition 1, 2, 3 can together obtain a value of 10. Okay. Then what can we do with this coalitional game? Well, Shapley was looking for what we call a value of the game, or a division of the game, in the sense that he tries to associate 3 numbers, 1 to every player, phi 1, phi 2, and phi 3 here, that associates a payoff to each member such that the sum of all these payoffs is equal to the value of the grand coalition. So in other words, he likes to ask, how can we redistribute this 10 among the various players 1, 2, and 3. So if you have a game with n players, of course, here you have n values to determine. So one idea could be that you share the total value equal in 3 parts. Then player 1, 2, and 3 all get 3 and a third, right? And these add up to 10, so that's one possibility. But of course, you would say, maybe we can determine the value or the share of each person according to what they contribute to the coalition. Here I just copy-pasted the different coalitions and their value. So let's assume, for example, that the grand coalition is formed by first taking individual 1, and then individual 2 joins the coalition together with 1, and then finally individual 3 joins to get the grand coalition. Then before player 1 arrives, there was nobody, and now player 1 arrives, and you see that the value jumps to 2. Okay, so here you can say the contribution of player 1 is actually equal to 2. When player 2 joins, before player 2 joins, the value was 2, but now 1 and 2 together can get a value of 7. So player 2 can claim maybe a value of 7 minus 2, whatever he contributed to the total value of the game. Okay, so here the contribution of player 2 is 5. And then if player 3 joins, finally, they altogether get a value of 10. Previously, 1 and 2 got a value of 7. 10 minus 7 is 3. So here the contribution of player 3 is 3. So one possible division could be that player 1 gets 2. His marginal contribution of 2 is 5. And then the marginal contribution of 3 is 3. And of course, these add up to 10. But of course, these are not the only possible ways in which the coalitions can get together. Another way could be that first player 1 arrives, and then player 3 arrives, and then player 2 arrives. In this case, player 1 still has a marginal contribution of 2, but the second step, 1 and 3, gets formed, which is a value of 4, so player 3 gets the marginal contribution of 2. And then when player 2 joins, they all get together 10. So 10 minus 4 is the marginal contribution of 6 for player 2. So we can basically go over all the possible cases in which people can join the coalitions. So you could have 1, 2, 3, and then 1, 3, 2, and then 2, 1, 3, then 2, 3, 1, and so on and so on. Okay, and every time you can determine the marginal contribution of each player to the formation of these this grand coalition. Ex ante, you could say, I have no idea how the coalition will be formed, who's going to arrive first, and then who's going to arrive second, and who's going to arrive third. So we could then take, for example, the average contributions over all possibilities for player 1, which gives the value of 3.5. And we could also average all the contributions of player 2, which gives 4.5, and then the average over all contributions of player 3 is 2. And of course, because this is an average of different things that add up together, 3.5 plus 4.5 plus 2 is equal to 10. Okay, and actually, these averages here are exactly the Shapley values. So how do we get to the Shapley value in the general case? Well, the first thing you need to do is look at all possible queues of players. Here we have 1, 2, 3, 4, 5, 6, right? These are basically the different permutations of the set of all players. And then for each player, you can determine the set of all the players that enter before I, here including I. Okay, so pi less or equal to I, these are all the players in N, such that in this ranking pi, j arrives before or at the same time as I. And pi less than I is the same thing, but now only the players that arrive just before I. Okay, so the marginal contribution for this ranking pi here for I is V of the set of players who arrive before I, including I, minus V of all the players that enter just before I. How do you define the Shapley value? The Shapley value is simply the average over all these possible rankings. How many different rankings are there? Well, there are n factorial number of possible permutations, so you have to divide by n divided by n factorial. Okay, so this is how you can define the Shapley value. You take the sum over all possible permutations, you take the difference in value, or you take the marginal contribution of player I for this particular ranking, and then you divide by the number of permutations. There's a different way in which you can write the Shapley value, so maybe we should also go over this now. So let's take a set S and let's think in how many ways are we going to write here V of S. Okay, so here we have to look at the number of permutations for which P less or equal to I is equal to S. So this means that for this permutation, all the members S minus I arrives before I, and then of course all the members not in S, which are here the members in minus S, arrived after I. And you would try to see how many of these, of all the permutations, how many have the property that all these people here, all these players arrived before I, and all these players arrived after I. Well, here there's S minus 1 number of people in the set. Okay, small s is here the cardinality of the set S. And in this set, there are n minus s players. So in order to count the number of permutations for which I is at this position, what we could do is we could look at all the possible permutations of this set here, of all the people that arrived before I, and then all the possible permutations of all the people that arrived here after I. There's s minus 1 permutations among all these players, and there's n minus s per faculty number of permutations of all these players. And of course, you have to multiply them together to get all the possible combinations. So how many times do we have a s appear here in this part? Well, it's s minus 1 factorial times n minus s factorial divided by n factorial. And here the same counts for v s minus I. So we can also rewrite the Shapley value as the sum over all sets S that contain I, right? So here S contains I, of s minus 1 factorial times n minus s factorial divided by n factorial of vs minus vs minus I, which is the marginal contribution of I to this set. So this is summing over all sets that contain individual I. To every set S that contains individual I, we can also uniquely identify a set that doesn't contain I. This is simply by taking the set S that contains I, this one here, and then throwing away individual I. Okay, this gives you a set T that doesn't contain I. And to every set S, you have a set T that doesn't contain I. And for every set T that doesn't contain I, you have a set S that contains I by just adding individual I. So instead of summing over all S that contain I, you can also sum over all T, all sets T that do not contain I. And then, of course, S minus 1 is exactly the size of T, right? So we have T factorial here. N minus S, well, it's N minus T minus 1, because T is one element smaller than S. So we have N minus T minus 1 factorial here divided by N factorial. And then V of S, well, that's the same as V of T union I. And V of S minus I is the same as V of T. Okay, so either you define it as summing over all individuals sets that contain I, or you can also sum over all coalitions that do not contain I, but then you have to readjust slightly this weighting coefficient here and redefine the marginal contribution of player I.